Okay, let's get started. So for those of you who are on Zoom and also the one in the class, from now on, I will occasionally take attendance to the in the class. So if you register for the online session, right? So if you go to online, that's fine. If you register for the in-person session, I will take attendance to see, because now it's come to the point where few students come to the student. I see familiar faces every time, but I think this is you guys come to the class regularly. I will take them. I'll see what I'm gonna do. You guys will be rewarded for coming class every time. Okay, so that's so like brief announcement. So, but I will probably not gonna do it for every single time, but once in a while, okay, I will have in take attendance. Okay, so we starting talk about the PageRank from last time. Today we're gonna finish it, and I haven't posted the project number 2 on the Brightspace yet, but I will do it on next Monday. So in next Monday, the project 2 will be posted. Then since I think a little bit let me just check in the schedule. I think okay. So I think it's let me just check my phone for the October 13. That's a fall break, right? I think October 13. That's a fall break. We don't have class. So so the assignment will be given out on October 6th, which is next Monday, and it will be due on October 15th. So again, this project will also have probably about like 9 days to work on it. And this is just to or maybe I can give you guys 10 days, or maybe make it due on like a Thursday or something. In that case, is because today we finished. You can have extra day to work on it. Today we're gonna finish the PageRank, the algorithm, and then next week we're gonna spend like 2 classes to talk about MPI for Pi, which is giving you how to implement the PageRank. So but I'm probably gonna cover majority of the stuff in the. Once you finish Monday's class, you should be able to work on the project. Okay, so on the next Wednesday, there will be something like a more advanced technique about MPN4 Pi. But the basic stuff we should already have all the available tools for you to implement the PageRank. Okay, so that's how we can plan out for the before the fall break. So then after you came back from fall break, we will start to talk about the more advanced modeling technique, and then how to implement them like in big data. We're gonna start with simple models like linear model, logistic regression. Right, so that's like the simple ones. Spend a couple classes on that. After that, the algorithm we're gonna talk about is the random forest, support vector machine, and maybe the gradient boosting, and particularly the how do you implement them using the big data technique. Okay, so that's sort of what's to come. Okay, so we talk about the PageRank. The basic idea for the PageRank is we need to first establish. This is a starting point. We're starting with the graph, right? So this is the page graph. In this graph, basically every web page is linked to another web page through an arrow. This arrow is directed, right? So this is also called directed graph, which means directed graph means the beginning and the end. You have 2 graphs. You have 2 nodes, node 1, node 2. So then the travel, so if you travel from node 1 to node 2, this is different from travel node 2 to node 1, right? So this is called directed graph. Another graph is indirect graph, which means just connection between the two. There's some connection between these two. So the PageRank is working on this so-called directed graph, where the direction is important. So once we have this graph, the first thing is to transition or convert this graph into this so-called transition matrix. Right? So transition matrix is representing if you have a node, so each row and each column representing a node. So if you have a node, you have a link from one node to another one, then corresponding position you would have in a value, right? Have a value representing transition probability. If you just have 1, 0 for every entry, that means that's more like for the indirect graph. So that meaning you having a graph in between. Camera position. Someone. Yes, I didn't realize that. Let me see. Okay, let me adjust the camera angle a little bit. So someone has every single time someone like change the camera's direction or remove the. Okay, I think this is it. Okay, thanks for reminding. For those who are watching online or during Zoom, if you have any questions, let me know. Okay, because like if you don't remind me the camera, I didn't even realize the camera was pointing to the class, not to the whiteboard. So I was saying the first thing is to construct this transition matrix. So transition matrix, then each entry, it will be represented probability from one node, from this node B to the node A, right? So the transition probability, and this probability is determining how many outgoing from this node, right? So it's basically if you have two, so for example, if from node B you have two outgoing links. One is to A and another to D. So therefore, you have 1/2, right? Half probability, 0.5 probability going to either node A or node D. So therefore, both this entry B to A and B to D receive like a half probability in this entry. If you have, for like another example would be A, since if you look at the A has 3 outgoing the links going to B, C, and D. So each of them, B, C, D, receive like 1/3 of probability. Okay, so that's the first step. Once you have this is once you construct this is the graph or having this is the value being represented this way, then one can convert into this transition matrix. Once you have this transition matrix, calculating PageRank would be just simply a sequence of the matrix multiplication operation, right? So you're starting with the initial vector V0. V0 would have in the entry of 1/n. Suppose you have n web pages. So 1/, that just means the V0 means when your starting point, you're starting from like randomly, right? You're starting randomly at each web page. Then after one transition, the distribution of the so-called web server will be just simply m times v0, right? So that's like the distribution at the beginning will be uniform across in all the web page is 1/n, and then after one step, the distribution or the probability for each the link the server is gonna visit is become m times v0. Then second step would be just multiply m again, m multiplied by the v1, which is m times v0. Now this becomes m squared v0, right? So and so on. So if you after n step, then or after t step, then it just be simply m the power t times v0. So that's a bt will be equal to that one. So the bt will be the would be the distribution or the probability of a random surfer is visiting a given node is according to this probability. Well, there are a few things. There are some theoretic guarantee. If the graph is strongly connected, then we can. The strongly connected means you can get it from one node to any other node, right? If you're starting from one node, you can go into any other node. Then this graph is strongly connected, and there's no dead end. So if I have that graph, after about 50 to 75 iterations, then we would have in some distribution close to sort of stable distribution or the sort of limiting distribution. This is basically the macro process, right? It's the satisfy macro. This is a macro property. So that means if you having a strongly connected graph and you randomly starting from the any node, if you travel it long enough, then you eventually gonna give you something stable, and that stability can or the limiting distribution can give you so-called the relative importance of each node, right? If you having the more probability to visiting a given node, that means that node is more important than others. That means everybody else thinking the node is important as a whole. So in order to do that, we need to deal with dead end. We need to a dead end that is relatively easy to solve. We just remove dead end. And we talk about structure of the web. We have to drop them sequentially. Then eventually we can end up with this is a strongly connected component. Another abnormal structure would be the so-called spider trap. Spider trap, that's where you have this is the node pointing to itself. It not only is a dead end, but also it's a keep pointing to itself. In that case, it's hard to just drop it. So in this way, we want to do is try to use some other mechanism, which is called taxation. I think this is where we stop. So taxation is basically saying, if you have this is a spider trap, right? Spider trap exactly is very hard to get out. And as I mentioned before, if you only have one node pointing to itself, that's kind of easy to identify. But you have in a small cluster of them, so you have 100 nodes, the web pages. They just doing they just connecting each other, forming sort of small the circle within the self. Then for those, it's very hard for you to remove them, right? So you for example, if you have a big, you have a big the strong connected so this would be your strongly connected component. This is you have 1 billion website somewhere outside, right? Now you can construct a local network. Local network is basically you want to have someone to point to this, someone point there, and then you just inside this one, you just point to each other, right? You form a local community. Then this local community also serving this is so-called spider trap, right? But it's not only one node, but it's that just basically means if you somehow get it from here to this one, then you're going to be trapped forever, right? Trapped forever. So this is also kind of the very sort of hard to detect. I mean, this could happen, right? Because you can if you're smart enough, you can construct 100 useless links. But if there's one page, you can make it very informative. So therefore, there's somebody going to reference to that one. So this is one website which is you make it sound informative. Somebody going to reference it, so that point to that. Once you get into there, from here you just point to other sort of the local. So this is create a perfect the trap. Basically, once you get in, you cannot get out. Okay. So to avoid this kind of the spam, this is not it cannot be done just by simply remove it, because it's again, if you want to remove it, you have to detect it first, right? If you cannot detect, how you can remove? The way to do that is we can we can do so-called taxation. Taxation, that is basic idea is also very simple, but it's a very powerful idea. That is to allow each random surfer a small probability of teleporting to a random page. Okay, rather than following an outlink from their current page, so the default setting is once you land the page, what you're going to do is going to go out of this is the next page you're going to visit is according to the outlinks for that page, right? Now, this is taxation saying I'm going to add in a small random probability, okay? To that is not only this can go into the outlinks of this web page, but it also has some small probability going to any page, okay? Any page. So in that way, it can solve it even if you're sitting in this small world, but you still have some chance to escape from there, right? So that's the idea. Now, the iterative step where we compute a new vector estimate PageRank V prime from a current PageRank estimate V and the transition matrix then is become like this. So you have some beta, probability beta, which is following your outlink, is M times V, that's essentially is following the graph, right? On top of that, you also have in the small probability E divided by N. So this would be the random part. Okay, this will be random part. You can think about this is basically once you have sitting on the web page, what you're going to do is you're going to have this is like become a two-step operation, right? You're going to have a dice. Okay, you threw a dice, and then this dice is going to have the probability of or the coin. Okay, the probability of head is equal to say beta. Probability of tail is equal to 1 minus beta. Okay, so you're gonna add every time you're sitting on a page, what you're gonna do, you say I'm gonna flip the coin. If it's head, I'm gonna follow the link. Okay, I'm gonna follow the link. The outlink of this is the web page is pointing to. If it's a tail, what I'm gonna do is gonna randomly, okay, I randomly jump to another page. Okay, evenly distributed. So then this is basically saying
randomly differently connected link on that page?
No, randomly to any page in the whole web to the whole internet. Yeah, it's not a. So this is basically saying if it's head, then what I'm going to do is I'm going to follow the density is mv t minus 1, right? So this is you're following, because when you are following this, essentially you are doing randomly on the outlink of this web page contains, right? Remember when we construct this transition probability, like this one, the transition probability, this is it landing on its outgoing links is like a random process, right? So because you have equal probability to each of the outlink. So that's so this transition probability is representing the but you're representing the random jumping to one of these outlink, okay, with equal probability. The second term, this right here, E divided by N, what is E divided by N? E is vector 1. This is just essentially 1 over N up to like 1 over N, right? So it's just saying if it's tail, I'll have 1 minus beta probability, which with each probability going like 1 over N probability going to every single pages in the whole net, right? In the whole net. This is like you are jumping to that. So this is called teleporting, okay? Teleporting to a random page. So what it does is it allows some probability to get out of the spider trap, right? So if you're trapped, if you don't have the second term, if you get trapped in the small corner, you're gonna stay there forever. But if you have the second term, even you are even going to into this is like C, you next step you still have some probability to get out to the rest of the world. Okay, so that's this is the idea. So beta is a chosen constant. Usually the beta is the beta could be is pretty large probability, like 0.8 or 0.9. Okay, that's this is for beta. That means in most of the time, okay, most of the time I'm still gonna follow the web structure, right? I'm gonna follow the network structure. But just with some small probability, like 10% or 20% probability, with 1 minus beta, that's equal to 0.2 or 0.1, right? With some small probability, then I will be able to jump out to the outside. So you can sort of think about you have every time you will have some like a random server at each step. You will have some random starting point. Okay, somebody gonna start randomly to that. You can think like, say, at the beginning, at the first step, you're gonna have like a say 1 million people was like randomly landing on the web, and they're gonna follow the outlink, right? So in the second step, you also have another like 1 million people randomly on the link, and then you're gonna follow that step. And on the third step, you're gonna add in like a more random the starting the starting server, and then eventually after like many steps, they can counting how many of them they got what's the distribution for how many people landing on each of the web. So that's giving you so-called a stable probability. So this is a taxation. Again, it's a simple idea, but it's a powerful idea. Okay, it's a powerful idea because once you have in the second term, then this is the spider trap is the idea is the spider trap is going to be a small percentage of the web, right? You cannot be large, right? You only be a small percentage. So if your web is large enough, get into this position, the probability is still relatively small. Okay, relatively small. So therefore, you don't once as long as it allows some probability to get it out, then majority of time you still travel in the rest of the world. But you do need to some mechanism to say once I get in here, you can get out. So this is a very simple. This is an idea which is I don't. If you guys are a little bit familiar with like reinforcement learning, this is kind of like the exploration versus exploitation, right? So it's kind of like you want to have some probability you can experience something new, right? This is part is kind of like exploitation. This is part is like exploration. So the idea is the same, which is you can which is I think it's also very useful in your life. Okay, in your life you should kind of you should try this formula in your as your life guide as well. For example, if you just want to try like go out to a restaurant, right? Go out to a restaurant. Now you after you taste some restaurant, you kind of have a few favorite restaurant, right? So then every time, then the next time when you want to go into detect this is a I want to go out to have a dinner, so you can say I can if you find one you really like, so every time you go into that restaurant, right? So that's you kind of trapped to that restaurant for forever. So in that case, you want to have some mechanism which you can get out. The mechanism could be you just go on the website to see the TripAdvisor or some like or the Yelp to find a local restaurant, random pick one, okay, random pick one, and then to see if you like it. In that case, you can that idea is also a taxation idea, right? So in that case, you can not all the time you can find a better restaurant, but then you can explore something new occasionally. Okay, give you some small probability, you may be able to find a good one. So like 80% of the time, you can go to your favorite restaurant or the few of them, choosing a small favorite restaurant. 20% of the time, you should just go try random place. Okay, so in that case, you will have some probability, give you some probability to explore something new, and also to getting something which may be better than because you don't know you haven't exhausted all the options yet, right? So you may still have some probability to find some the places which is better than your current favorite. So that's in that is like this is also kind of follow the 80-20 rule. You guys, I don't know if you guys know the 80-20 rule. So it's kind of this is if you think about it as all kind of this is things are kind of all related. You 80% of time your favorite, 20% time risk. Okay, try some risk. In that case, you're gonna benefit with in the long run. Okay, it will broad up your choice of the selection. In the work is the same thing. Okay, if you're doing like if you in the future, once you go out to the like say go to a company starting working, you should also follow this type of rule. 80% time do something you're good at and you're comfortable with, and then 20% of the time you should take some risk. Okay, to explore something new, to find some project which is you're not that comfortable with. So this can build up your long-term the career path as well. Anyway, so this is just I'm just saying this is this so-called idea of taxation. It's just a formula from this is from the slides. But if you really think about it, it actually makes sense, right? It actually has some I think it has some wisdom into it. Okay, so it can if you really want to break it down into this component, this is actually applied to many aspects of the life. Okay, so the taxation is once you having this is so-called random once you have this is called a random jumping or the random the component into it, then this is so like the not the last bit, but this is so like a solve one of the most important the issue in the PageRank. Now this essentially this is the last this is the formula for the transition, how you can do the transition. Now but the only issue now is used to be we will have the as I mentioned to you, if you have VT equal to MT to the V0, right? So the calculation could be easier. The calculation is easy because in order to calculate this statement probability, what we can do is we can say we want to calculate M to the 64. Then basically this can be representing M times M will be equal to M squared then times yourself to be M4, 4 to the M8, and so on. M64 would be like 6 steps, right? It will be very fast. Now your VT is become beta times M times VT minus 1 plus 1 minus beta times E to the power of N, which is this is V0. Okay. E over N is V0, right? This is your starting point, is your V0. So in this case, you have when you have in this, if you do the iteratively, then this will be equal to beta times this T minus 1 will be beta times M VT minus 2 plus 1 minus beta V0 plus 1 minus beta V0. So you can, as you can see, this will become the calculation for this probability can no longer follow this simple like the binary the expression, right? But instead you have to calculating like every you have to calculate like all the let's just finish this one. T minus 2 plus beta times 1 minus beta V0 plus 1 minus beta V0 and you have M here. Beta times M V0 So you're gonna have this is this kind of the formula, which making the computation a little bit harder, okay, a little bit harder, because now you cannot take advantage of this is just simply do this the power the expression and more. Rather, we have to calculate this is we need the m. We need m squared, we need m to the cube, m to the power 4 and 5 and so on. Which basically essentially each step we have to do the do the power for of the m at every single step. But that's okay. Okay, it just basically means it's it just more computation work. Okay, but still not that difficult. So then the next thing what we're going to do is we're going to see how we're going to implement it. Okay, so the page if you want to use PageRank in a search engine, so each search engine it actually has a secret formula that decides the order in which to show pages to a user in response to a search query consisting of one or more search terms. So Google said they have over 250 different property pages from which a linear order of pages is decided. So in the search engine is a big business, right? It's a big business. Some of them you can purely is a content based. How do you display? How do you display? This is the order pages. It's not. It's actually the top secret of the search engine, right? The company. I don't know in other places, but in some search engine, okay, they can use so-called fee-based search engine. So they are using PageRank. They are in the backend, but at the same time, they also consider like people are paying for the keywords. Okay, so whoever getting like paying the highest which is I think it's unethical, okay, for some terms. But that's how the business run. Yeah, Google also having this is it's called AdWords. It's kind of like similar. Okay, some AdWords used to be in a like a final project. People are doing this so-called AdWords. The group as a group project, right? So people can actually see that. So this year again, I haven't made up my mind for the final project yet. So maybe you're gonna see or may not see the AdWords algorithm, but it's a way. Basically, the point I want to make here is how to rank them. Is the page rank is just one piece of formula. Okay, is important input to the ranking. But how do you decide within that way? How do you decide is actually more complicated. Now, in order to be considered for the ranking at all, a page has to have at least one of the search term in the query, right? Otherwise, it wouldn't make sense. So this is the first. This is like the first the thing. In order to display, you cannot just display a page which doesn't consider your search term. That doesn't make any sense, right? So normally the weighting of the property is such that unless all the search terms are present, a page has very little chance being in the top 10 that are normally showing first to user. And among the qualified pages, a score is computed for each. And the important component of this score is page rank of the page. Other components including the presence or absence of search terms in like prominent places like headers or the link to the page itself and so on. All right, so this is we can calculate in this the page rank. If you look at this, right, the page rank, this calculation does not depending on any terms at all. It's independent of your search terms, okay? Right, because what it says is it only determined by how this is the web pages are linked to each other. Okay, so they are so far we are having the value here is independent of your search term. It just represents the importance, is more like the importance of that web page in the whole website, right? In the whole website. So when you do the search, okay, when you do the search, you're gonna limit yourself. You're gonna say you search a term, say like
Apple computer, right? So or the iPhone, or whatever you search a term, then there are so many web pages, see like 10,000 web pages contains the keyword iPhone in there. So among this 1,000, or the 10,000 web pages contain your keyword, then you have to rank them again through some mechanism, right? So that's yeah. Search term, that depends. That depends on the how you design. That's where this is one of this is where is this? This is one of this is 250 different property. This is where this come from. Okay, you can consider you don't consider that's that's outside of the PageRank. Okay, so first thing is you want to extracting a small group which is gonna have the contains your keyword. That's what a small group is gonna work with. Then the second step would be you want to somehow rank this is small group, right? Then one of the component to rank this is a small web pages would be the PageRank. Okay, PageRank. That's will be this kind of important. Others like this other component be whether if you term like in the header, you're gonna have a better score. If you have in this is you may have in this is called the bag of words, right? So if you this is a like you have two words, they are together. It's together in your search sequence. They may be it will be like more give you more score than the separated part and so on. So there are different ways you can sort of like optimize your search. That's a different company, they have a different formula. So again, the PageRank will be one of the important the component of it. So the next thing we're gonna see is how do we implement it. The implementation is we're gonna talk about the two implementations. Okay, so the first implementation is just purely based on the matrix multiplication. That's which you already covered. Now then what you have here is essentially is not different from what we talked about before about matrix multiplication. The second implementation is more just related to the web structure. So we're gonna see the second one actually is a preferred one. Okay, so we're gonna talk about both. So the first implementation basically is we want to construct. We're gonna construct two tables, right? One is current, one is next. This table holding the page ranks for each page, and we're gonna seed the current with the initial page rank values. So the seeding will be just V0, right? So V0, in this case, the V0 is equal E over N. N is total number of pages. Essentially, is 1 over N, 1 over N, up to 1 over N. You have N of them, right? So this is your starting point. You're gonna see the current. The current is equal to the V0. Then you're gonna iterate it over all the pages in the graph, distributing this page rank from current into the next link keys. Okay, so and then we're gonna setting the current to giving the next to the current, and then we're gonna the next we're gonna get a fresh table based on that. Then we're gonna go back to the iteration step and until it converges, or until we have in the certain iterations, right? So you have like 50 iterations or 75 iterations, whatever, and then, or it's converged. We're gonna have in that. The convergence, okay, convergence is actually typically very fast. You guys are gonna see in your project in the second project, what are you gonna have? We're gonna not gonna have billions of web pages, but have millions. We're gonna have in some level is so we're gonna give you is like a 1 million website, okay, and you're gonna have in the link to each other, and then as you're gonna see, it only actually taking. You're only taking like probably 4 to 5 iterations, okay? Then you're gonna see your distribution actually become very stable. It doesn't even go to like 50 or 70. So you can try is actually plus we don't have that bandwidth for you to run like a 100 iterations for that large of network. So you can see after like 4 to 5 iterations, it can actually be pretty stable. So the distribution of algorithm, the key insight allow the parallelization is the next table is dependent on the current, but does not depend on any other rows of next. Okay, so then this means individual row of the adjacent matrix can be processed in parallel. And this is sparse matrix rows are relatively small. These are the key things we can allow for the parallelization. And the key consequence of the insight is we can map each row of the current to a list of PageRank fragments to assign to linkages, and those fragments can be reduced into a single PageRank value for a page by summing up. Then lastly, the graph representation can be even more compact, right? So you can search each element is simply 0, 1, only transition column numbers where you have 1. It's probably a little bit hard to understand from the work. Let's just see how if you see the graph, you're gonna see this is pretty easy for you to understand. Now in here, the right hand side, this table is your next table. Okay, this is your next table, and on the right hand side, this is your current. Right. So your next the URUNT. It's not easy to oh. So this table is current. What you're gonna do is we want to having this M is the transition matrix, right? This is your M matrix, your transition matrix. So you want to generate the next table based on the current table. So what you can do is essentially, or what is saying here is like here. So the next table depending on the current table, but not on any other rows of next. That means, for example, like this is a V1 prime, right? So this is the component of the next table. It depending on the current table. It depending on all the entry from the current table, but it does not depending on any other rows of next, which means calculating V1 prime does not depend on V2 prime or the V3 prime. It's not sequential, right? So this is essentially is the basis, right? Why you can parallelize them. So in this method, we use like a key square of the map tasks, each task getting one square of the matrix M, say Mij, and one stripe of the vector V, which must be Vj. So what you have here is you can have, if you have this square matrix for the M matrix, you can sort of like divide them into key. So you divide them. This is to the key component, right? Key fragments on the rows and key fragment on the columns. So therefore, totally you have key square. This is a square matrix, right? And then each one piece of them, it can be multiplied to one of this is the current table. You can also count 1, 2, 3 up to like a key fragment, right? It's corresponding current fragment. So therefore, you can do what we can do is M11 times V1, M12 times V2, M13 times V3, and V4 times Y4 times V4, and so on. So you can have in basically generally this key square the map task. But in here, what it does here essentially is it can be the matrix M can be dense. Okay, it doesn't have to be sparse. You basically just carve this is your matrix into like into this small square matrix, and this small square matrix, and then can be multiplied by this guy. Now, once you have this, then this is a V1 prime, the new fragment in the next table. V1 prime just essentially is this M11 times V1 plus M12 times V2 and M13 times V3 and M14 times V4, and they sum up just like matrix multiplication, right? So but you just doing in a batch cases. So in this case, you can basically do the making the summation using the MapReduce framework to implement it. So you have m k square m tasks, and each task computing one piece of this the small matrix multiplication. So once you have in the reduced part, essentially just sum it up, right? Just sum up to the different part. So if you want to represent in the graph, this is just saying in the map step, we're going to break the page rank into even fragments to distribute to the link target. And then in reduce step, we add together fragments that into the next page rank, right? So this would be the corresponding page rank. And this is mapping in the map step. Essentially, is just this, right? We do this guy in the reduce step. We just sum them up. Okay, so that's how it this is how it works. Now, if you want to putting up order the job into like a one in here, that is we need to do for the page rank. What we're going to do in the phase one, what you're going to do is we're going to pass HTML, right? So this is where we map the task. The map task going to take in the URL, the page content pairs, and then map them to be the URL, which is your this is identification ID for web pages, right? So this is URL, this is your ID, and then you have in the PR initiate the page rank initial value. This will be the seed. This PR could be if you have like 5 outlinks. This will be 0.2. You have like 2 outlinks. This will be 0.5, right? So you're gonna seed in your page rank value, initial page rank value, and then each one also contain a list of the URLs. This will be its outgoing links. So then the reduce task is just the identity function. This is where you have this is the parsing the HTML, creating this link. Now once you have this, the second page rank distribution, the map task is you can take in your URL, the current ranking and the URL list. Then this is actually so this is actually the this from here. This is actually the second implementation already. Okay, so let's just see from here. This is your second implementation. Second implementation, because the first implementation is you're gonna construct in the you're gonna construct the transition matrix, and then you build up this is the matrix multiplication, right? That's depending on using the matrix the multiplication and that technique. Now the second implementation it will be you will still have in the concept of the matrix multiplication in the backend, okay? But now we're going to be more explicit on the web structure and try to use in the web structure to do the job. Now, in this, okay, let me first describe the algorithm. Okay, so then we're going to walk through an example. So then you will be able to understand this is the second implementation actually better. So the second, now you pay attention to this one, okay? Because this will be the method you will be the method you're going to use for your project number 2. Okay, make sure you understand this is this information. So what do you then in the first phase? What you're going to do? What you want to construct is you're going to construct an ID, make this pair ID, which is say you have URL. Let me just use 1 or 2, okay? Because this is just representing this is unique ID for each web page. So in the first case, you're going to have say the initial value of So in the first one, you're gonna have in this here unique value actually not for you. This is 1 over n. That means for the first 5 pages, say for a simple example, okay. So like say I have five pages, okay, 5 pages total. Now this is my web page number 1. I'm gonna have in my initial page rank is gonna be 1 over n, right? So this is gonna be 1 over 5. This is my initial page rank value, which is given like this. Now suppose I'm outgoing, then from the page 1, we're gonna have in the list of the outgoing, say it's gonna go into 2 and 3. Okay. So this is for the page 1. For the page number 2, I also have in this is a same initial page rank 1 over 5. Now from 2, I'm pointing to 1 and 3. Okay, and so on. So what are you gonna in the first step? What you're gonna do is you're gonna constructing this information, which is having its URL, which is ID, and the list of the URL it points to, and also its initial value. This information alone is what it contains everything about the transition matrix, right? Because it tells you from the one link where it goes to, right? You can point to, and also what is the entry for them. Okay, so this information along here, from this information, we can derive the transition matrix M, right? Transition matrix M. You already have this. Now, then basically the first step is here. Although this is called parsing the HTML, but it's also can be saying this step is also like constructing M, constructing a transition matrix. Okay, yeah, this is essentially the same thing. Once you're having this is a transition matrix you're parsing this HTML. So the second phase will be the page rank distribution. So map task, what you're gonna do is the map task can take in the URL. This is like the first step, right? You have this key value pairs from the first phase. Then for each view in the URL list, then you're gonna emit key value pairs. The key value pairs will be view and the current rank divided by the URL, the number of the elements in the URL list. Okay, so you're gonna emit the key value pairs is the URL and the URL list to carry the points to the list along the iteration. Now what you're gonna have is from here. Okay, let's just say now this will be the. Let me just do one more. Okay, do one more. So in that case, we can do 3. Then starting point is 1 phase. Then from 3, you can say point to like a 1 and 4. Okay, so this is the key value pairs. Now what you're going to do is in the second phase, what you're going to generate is 2 things, right? One is going to keep the URL 1 here, and also is a social list. You want to keep that information because this is going to give you the outlinks, right? For that, you want to keep that information. This is the web structure you keep it. You also want to emitting from this phase. You're going to from first record, emitting 2, and basically is so you have 1/5. So that's 1/5 times half as well. Because what it does means is from the link 1, you're going to have 1/10 of probability going to link 2, right? Because you have 1/5 of probability sitting in the link 1, right, or page 1. And for this 1/5 of probability, you're going to see randomly, you're going to evenly spread to the 2 outlinks, right? So each of them get half of it. So therefore, the 2 from link 1, the 2 is going to get half of probability, half of the 1/5, right? The probability. So you all have this probability. Then you also get the same thing for the page 3. You also get 1/5 times 1/2. Okay, so you have so therefore then for the map task from this first key value pair, that's the three elements key value pairs you're gonna meeting from there. For second pages, what you're gonna have is first you're gonna keep its web structure. Right, so 2 and its URL list, you're gonna keep that. Then you're gonna have in 1 or 1/5 times 2 times half. Then you're gonna have 3 1/5 times half. Right, so you're also having from page number 2, you having the same probably go to 1 and the same probably go to 3, right? So you have this. Then for this one, you're gonna have 3 it's web thing. You're gonna have 1 or 5 times let's say just 1, okay? That's just not everything. So let's say on the for number 3, you only have one element, okay? So you have let's give it's all probably to 1. And so on, right? You should have like a 4 and a 5. So in the map task, right, in the map job, okay, the map job. So you're gonna emitting this things is gonna emitting. You're gonna emitting the URL and the URL list itself to carry the web structure, and you're also gonna emitting this is U and the current rank divided by the number of elements in the URL list, right? So this is what it has. Now in the reduced task, okay, in the reduced task. So what was in the reduced task? What you're gonna do is you're gonna get in the URL list first, and the many of the URL with its values, right? So let's see for the let's just in here for the key value 1, which is now this is at the reduced step, right? For the URL 1, what are you gonna have? The value is gonna collect into it. You will have this probability, which is you're gonna have in the first thing you're gonna have 2, 3. The links, right? The URL list is point to the out links from 1, and you're gonna also have this is a 1/5 times half. This is from here, and you also have this 1/5 from the third, right? You want to have these values, okay? Now, this is the input for the reducer. Now, input for the reducer, what you're gonna have? Reducer is gonna have is 1, okay? What you have now, the probability, the page rank value for the node 1 essentially is become this summation of these 2 probability, right? Because you have 1/10 of probability coming from node 2 and the 1/5 of probability coming from node 3. Assume 4 and 5 does not point to 1. Okay, so therefore, then this is probably become 3 out of 10 is 2 and 3, but it's outling and become the new key value pairs. Okay. So this new key value pairs can be serving as the next round of the calculation. You just realize, right? We now have the full so like a full cycle already. I think I have I have a typo here, which is I don't know why I didn't. Okay. Okay. Anyway, so what it does is so the reduced task is getting the URL list and the many URL values. Then you sum up these values and then fix up with D. What I'm doing here is the only thing what I didn't do here is this is still the following the page rank, the outgoing links, right? But if you want to, as we said, we want to add some taxation to that, right? Adding some taxation to that. So the taxation will be instead of just sum up, all the probability. So this is the probability 10 over there. So if you want to say the probability of a certain the page rank of the certain value. So you have a page rank. The page rank of the first node is going to be equal to this is a 1/10 plus 1/5, right? So this which is a 3 or 10ths. This is a probability if you follow the link, right? But now if you want to do the taxation would be, remember I have in the probability like a point, say the beta, now the beta is equal to 0.8, okay? So I'm gonna have in the 0.8 probability following this outlink, and I also have in 0.2 probability following random surfing, okay? So random surfing in this case is that if you have 5 pages, then the random surfing essentially is 1/5, right? Is 1/n. So I need to have in this kind of probability. So which is this will be 4 or 5 times 3/10 plus like 5/1 times 5/1. So this is 2, 5, so this is 6, 7 out of 25. Okay, right. So instead of this is a 3/10, here if you're using the taxation, using a beta equal to 1 the 0.8, then the value from here should be 7 out of 25, right? 7/25. On the slides, okay, on the slides there's a typo. You guys, you should fix it. The typo is in here. It shouldn't, like, this is D, essentially is beta, is a probability. I'm following the link follow. So the typo is, let me fix the right here in the side. I'll up the new version here. This should be 1/d times 1 minus d times 1/n. Okay, I missed 1/n here. Okay. So if you don't have 1/n, the whole thing is gonna be bigger than 1, which is gonna your transition is gonna blow up. Okay, you're gonna see is you're not gonna have the right value. So fix your slides. Okay, so fix the slides. You're gonna have 1 minus d times 1/n in here, or you can basically here is just divided by n. Okay, this is divided by n. That's also the same thing. Okay. I will upload a new version to the Brightspace after I get back to office. Now, once you're having this is from reduce step. Once you have this URL for the new page rank, new rank, and the URL list, then you can go back to starting a new page rank. The phase 2, right? You can have another map reduce the task and make it work. All right. So any question on this? Is this clear? Yeah.
Could you please repeat in the reduce step, which step did you summarize from the mapper?
Repeat the reduce step. Yeah. So in the mapper, you're gonna initial. This is, say, for example, for the page 1, right? You're gonna have it's the page 1, and also it's really the outlink. That this is clear, right? So then you're gonna have it from other places. You're gonna have in the 1. You're gonna have in the some probability getting to 1 to there. So then, in order to get it reduced, this is the input. Okay, this is for the reducer. The input, what you're gonna have is gonna collecting all the elements with the same key and put it into a list, right? So in this case, the input will be have the key, see the page 1. Then the associated list of it will be having its URL list to the 1, which is coming from here. Right, you have that, and you also having additional values. These values, which will be coming either from other links. In this case, you're gonna have 1 is from page 2, which is this side. Another 1 is from the page 3 on this guy. Right. Now, once you have these 2 values, then the next step is to update the page value for the page 1. So updating would be you can use the taxation method. Taxation method depends on the taxation, basically saying the new page rank will be equal to beta times m times v vp minus 1 plus 1 minus beta times 1/n, right? This is taxation. It will be this. Now, if you follow m times bt minus 1, which is going to be these two values added together, because this is where you have this. So therefore, then the beta times 1 over 10 plus 1 over 5, this will be this component. Okay, this will be this component. Now the new random component, which is 1 minus beta, is 0.2 in this case. And since you have 5 pages total in total, so the random landing will be just 1 over 5, which is giving you 0.2 times 0.5, right? So 1 over 5. Now the final results will be 7 20 out of 25. So therefore, for the page 1, you're gonna have in the page 1 has new updated page rank value is 7 out of 25, and also its associated structure with these 2 and 3. You do the same thing for every single link. There you're gonna have, then you have 2, 3, 4. You all have a new set of, this is a new set of URL and the page rank and the URL list, right? And then this essentially would be the input for the next MapReduce. So you can go back to the essentially, well, once you have this, then you can go back to here and iterate again. You have in like a second step and a third step and so on. Okay. Okay, so but here I have a typo on the slide. So this is very important. You need to fix the slide. This is divided by n. Otherwise, if you use this formula, if the wrong formula for the project 2, you're gonna be you are not gonna have the right results. So make sure. Okay, this is I'll also probably need to make an announcement in the course website as well. But any question on this? Is this clear? This is good. All right. Now, that's essentially is a page rank, okay, and its implementation. Now, there are some other so like the details about page rank, because ideally, each user should have a private page rank vector that can give the importance of each page to that user, right? Because you although we are starting with like a sort of random surfing, that means just didn't consider the everybody, right? Like each person should have in some kind of like a surfing or the web, when you visiting the web pages, each person should have in certain preference, right? So for some of you, is more like for most students in this class, we are like STEM class. I mean, some of you may like arts, okay? You may visit like art website, but I would say your chance of visiting the Wikipedia or some so like the tech website will be have more chances than art website. Okay, vice versa. Someone who study English or studying like the painting, they will never, well, never say never, but they probably have less chance to visit math website, right? So essentially, the random surfing or random starting point that's like applied generally to everybody is you couldn't go too wrong. But ideally, okay, ideally, each person you should have in your private page rank, right? Because based on your history, based on your preference, your starting point may not be necessarily be the same as another person. So each person should have in its own page rank. That's my ideal case. But it's just yeah. Say that again.
Why is page rank a search algorithm and not a recommendation algorithm? Each of us are going to have our own page rank.
Ideally. So I think this is the PageRank search algorithm is it's really I shouldn't say it's a recommendation algorithm, okay? Because what are you going to use for the PageRank? You are not using basically for the searching. Searching is done by by matching the items, right? So then once you have in this group item, so the page rank will be a very, very important metric to rank the pages. So it's kind of like the review system or recommendation system, indeed. What I'm saying here is once you have in this small website, okay, small like 100, then you have to rank among, let's say like 10,000 pages, you have to rank among them. Then the value, it should be like a more like a user like a specific, right? Because you know if you this is a 100 or the 10,000 or 100,000 web pages, then you as a user, you may have certain preference to some small group. So that's what I mean. Okay. So it's indeed it's not the search part is done, has to be done by crawling the website and also matching the key terms. That has been done. But on top of that, you also need a page rank value to also like sorting the pages to give them scores, right? So that's what I mean. Now, but it's just just not feasible to store a vector of length for many billions of the web page and for like billions of users, right? That's just too much. Now, the sort of like the compromise or the small compromise they call the topic sensitive page rank approach. So this topic sensitive is we cannot create a unique things for everybody, but we can probably create a the relative page rank for each group, okay, for each group, right? So people to I don't know if you got like a zodiacs, right? I don't know if you guys you're interested in that. Is the people classify different people by their zodiacs, right? So they say you belong to this, you have certain like characteristic and other characteristic, or your blood type, right? Your blood type A, B, O, and AB, they have different things. So they kind of try to see is that we can sort of like broadly speaking, we cannot give you like each individual unique or the page rank value, but we can probably sort of like group them, right? By using the different if you're searching like in topic of science, then it's probably then it's different from the search from the sports, right? Or from the music. So in that case, if you can generate some kind of the so-called topic, okay, certain topic value, then in that case it would be you can make it this is a little bit more the preferred to a certain group. Now this is so the topic sensitive page rank approach created one vector for each of the small number of topics, right? Biasing page rank to favor a page of that topic. So where we should lose some accuracy, the benefit is that we store only a short vector for each user rather than an enormous vector for each user. Now suppose S is a set of integer consisting of the row and column value of the pages we have identified belong to a certain topic, right? This is called the telepotent set. Now let the ES be a vector of one of the component in the S and 0 being the other component. So the topic sensitive page rank is given by this formula. You can see what it says is actually not that different from you've seen before. The only thing the difference is this, okay, is on the when you do the teleporting. Because on the teleporting, it would be if you are think about it, right? So if for a given individual, you have the chance to start randomly surf on the website. But at the same time, you may have zero probability of visiting like probably 90% of the website, right? Think about your browsing history. You probably like 90% of the website, or even more, probably 90% of the website. You never visit. You only visiting a small certain number of websites, right? On the web. That website will be your own like the small word you're gonna favor. So this ES essentially is capture that, okay? For a certain topic, so when you do the random surfing, like you can first term is you can follow the web structure, you sort of like surf the web. The second term will be saying when you are jumping out to a random web pages, instead of jumping out to the whole web, you're only jumping to a small portion of the web, okay? And this small portion of web is gonna be your preference, right? Either your personal, ideally this will be the personal preference for everybody. But in reality, what it can does is this will be will be just like a small subset for each topic, right? So you can classify this will be the TF-IDF is important, is coming to play. You can sort of classify all the websites based on their content to a certain topic. Then this is saying we can. So what it does is, so the ES, what it does is you're gonna have, so the say the number of ES is NS, right? So the see if you can see. So the number of, so you're having a small topic sensitive, the small web, and then the number of the website in there is NS. So you can have is 1 over NS for some of them. So this is 1 over NS. So this will be your for the set of S. You're gonna have in this is 1 of S. For the rest of them, just zeros, because you assume you have no chance or have no interest in to other website, right? So in that case, it's going to basically limiting your focus, your search, or the focus your ranking just within this small set. When you do the ranking, you are not doing. I basically saying I don't care about the rest of the world. I only care this is a small subset, maybe just 1% of the whole structure. So in that case, it can like force you to, when you do this do the ranking, you're kind of more force yourself to the ranking within a small subset, right? So that's could be more accurate in the one. You can see the only difference here is in the general PageRank, what it does here, you don't have the S, right? You don't have S, and this is divided by N. That's the only difference. So then using this, the PageRank, the so-called the algorithm is still the same. And then if you make some small modification, it can make it to be like more relevant to your search. So the quick conclusion basically is that map readers can run the heavy lifting in the iterative computation. The key element correlation is independent PageRank computation in a given step. And parallelization requires thinking about the minimum data partition to transition and so on. So even implement today, showing today doesn't actually scale the whole internet, but it works for the sort of intermediate size graph. As you're gonna see for the project number 2, this is what you're gonna do. Okay, so I'm gonna give you a small the graph like a problem like 1 million, okay, 2 million. The node is relatively small, but it's a decent size. Okay, so you can actually run through this algorithm to see how it looks like. Okay, for those of you, I will say again. So the project number 2 will be given out on Monday, and then just so you'll be prepared. So you will be given out on Monday, and then due date will be the following Wednesday, because October 13th is fall break. Okay, I'm going to extend to the next day. Okay, any final question? Any about PageRank? Okay. All right, that's all for today. I'll see you guys on Monday.